Yeah, Thibaut, Dumont.
Okay, thank you. So, hello everyone, I'm Thibaut Dumont. I'm a postdoc at Strasbourg in France, and I will discuss about the evolution of the abundance of lithium in the Loma stars. So, to introduce the topic, here you have on the right a plot with the abundance of lithium versus the edge, where you have on the top left the primordial lithium abundance, and on the bottom right the abundance of lithium in the sun. And as it was already said before, what we observe is lithium depletion with the evolution of stars from young age to the edge of the sun, basically. And so actually that is the witness of some transport in the stars and some transport of chemicals. If we extend to other stars, we have here a similar plot with the lithium versus the effective temperature, but for open clusters at different edges and different metallicities. And what we see is that in addition of trend of depletion of lithium with time, we have a trend with the effective temperature or the mass, with basically the low mass stars, which are more lithium depleted than the more massive stars at the same edge. But of course, we have as well some peculiar thing with here the so-called lithium dip that appears for the ads and Platypei, where here we don't, it doesn't respect this trend between lithium and the mass, and where basically we have strong lithium depletion, which is not similar to the rest. But the second thing, and finally, it was already said, but we observe an anti-correlation between lithium depletion and rotation velocity. Thank you. Okay, so in order to explore all of that, what I did is to do some stellar modeling using the stellar evolution code star evol, which allows me to test different transport processes in order to see if I can predict this observation and what are the transport processes that I need. So here on the left, you have the same plot as before. On the top of which I added some prediction from the models. And first, you have two gray models on the top, which are actually models which consider only convection or only convection and atomic diffusion. And what you can see is that even if you have a depletion during the prime and second, due to the convective zone which is deep in the star, actually it's not enough to produce the open cluster, the lithium in the open clusters, and the lithium of the sun. And actually, we understood with the anti-correlation with rotation that actually we need a transport process linked to rotation. So it's what I did just after, where I added in my models differential rotation according to Zan and Meder and Zan, which basically lead to a meridional circulation between the pole and a shear induced turbulence in the radiative zone. But what is important to know for that is that here I'm computing 1D stellar evolution code, 1D stellar evolution models, but of course rotation is a 3D process. And here actually I have different prescriptions from 3D MHD models, which give different prescriptions for this shear induced turbulence with different efficiencies. And you see, if you come back on the plot, that depending on which couple of prescriptions I'm using, the depletion of lithium that I will predict will not be the same, and it will be not the same interpretation from what you need for the lithium depletion. But what we can see already is that if you look at the vertical shear, here I'm testing two different ones, and we see that the purple and the red one are very efficient to deplete lithium, whereas the green one and the blue one are a bit better, and actually the green one is almost able to reproduce the lithium depletion. We would just need kind of additional turbulence in order to be a bit lower. So that's the first thing. But speaking of rotation, actually, we need to pay attention to the surface rotation of stars, but also to internal rotation of stars. And actually, for this low mass stars, we have the luck to have the sun. And here we have the rotation velocity versus the radius, so profile at the edge of the sun, where you have the four different models in color, and where you have in black actually the constraints from helioseismology. And you see that if we need rotation, the rotation that we use in the models predict a fast rotating core, which is very far from what we observe thanks to helioseismology. And basically here we need an additional transport of angular momentum from the core to the surface. And to do that, we can simulate this transport angular momentum adding a parametric viscosity, which allows, as you can see on the right, to obtain a flat profile as it is observed in the sun. But of course, that will impact the lithium depletion because basically it will counteract the vertical shear, and so it will, doing that, you will need an even more important turbulence in order to destroy lithium. But at the end, if you consider the rotation with the couple of prescriptions which was already cleared, adding 3 additional transport, you manage to reproduce very well the lithium observation. What you have here on the top left, you have still the abundance of lithium versus the edge. You see with green circle, like actually using a penetrative convection during the pre-main sequence, dependent of the rotation, we managed to deplete lithium enough to reproduce the lithium in the young open clusters and to obtain the anti-correlation between the slow and the fast rotators. And then, in order to reproduce the sun and the solar twins, using a parametric turbulence in addition to rotation, we managed to produce that very well, keeping the surface rotation and the core rotation constraint very good, as you can see on the bottom of this plot. So that is very good. And actually, here I can mention that similar models were done by Eggenberger et al. Using some magnetic field instability, and they obtain similar results. Because the thing here is always to identify which process is at the origin of all of that. Okay, so as I said, that was for a part for solar type stars, but if you look at stars with different masses, for instance, here in Zelyadis and Parisipae, we see that with the blue model, which are actually the model that I was discussing just before, the blue model are reproducing here for the lithium pretty well the G-type stars until you reach the lithium deep, which where you don't expect almost any transport with the same model because the convective envelope is very thin, and actually you need a different efficiency of the transport in order to explain this lithium depletion. So what I did here, as I said, depending on the prescription for rotation you use, you have different efficiencies. So I tested one of the strong efficiencies to reproduce the lithium depletion, but you see here that you are more or less wrong everywhere. But still, it's a step because actually you can say that, of course, you need a stronger efficiency, but depending on the mass of the star, the efficiency of the transport will not be exactly the same. And actually, here, coming back on the transport of angular momentum, you can actually calibrate this additional transport in order to control the lithium depletion. And you see that doing that, I managed to reproduce the lithium deep for the F-type stars and the G-type stars at the same time. And it's actually quite interesting because if you look at a physical explanation of that, we can invoke the internal gravity waves because we see that internal gravity waves are planned to drive angular momentum transport at a maximum efficiency close to 6,000 Kelvin, which is actually what I obtained in my own model at 6,000 Kelvin for more or less 1.2 solar masses. So that means that here, internal gravity waves could be a promising interpretation of this transport. But of course, it's as for magnetic field, it still has to be looked at, further explored. Okay, so now a bit to make the transition almost with the next session. Actually, I discussed about pre-main sequence lithium in the pre-main sequence and in the main sequence star, and it's actually quite important because depending of the amount of lithium you will destroy during these two first phases, it will be important when you reach the terminal edge sequence, because it will determine what will be the amount of lithium you will have for the more evolved phases, subgiant branch and red giant branch, and then it will be important, for instance, to determine the lithium-rich giant threshold, which is actually dependent of the mass and on the metallicity. Okay. And to conclude, here I wanted to say a few things. First, that if you want to reproduce lithium, actually, it's important to reproduce simultaneously the constraint for the chemicals, but also for the transport of angular momentum, because the transport of lithium is linked to the transport of angular momentum in the star. And so you have the constraint on the rotation and on the chemicals. Here, I showed that I developed a kind of optimal model, which actually worked pretty well to produce the surface lithium abundance for F-type and G-type stars and solar metallicity. But here, I'm showing a work done by one of my colleagues in Geneva, who actually, using the same kind of model, but little weaker turbulence, managed to reproduce pretty well the spike plateau and to explain the dispersion of lithium going from top 2 to top 1 stars, as you can see here. And the last thing I wanted to say that all of that is very nice. So the models seems pretty robust to give good prediction for lithium. But as I said, the mixing efficiency is mainly dependent on the rotation, and the rotation used in the models are dependent on the 3D dynamical prescriptions. And so it's arise a kind of uncertainty in the models. And finally, a few outlook. As I said, it would be important now to explore more deeper the transport processes, which are the origin of all of that, with mainly, as I said, magnetic field instabilities and internal gravity waves. Sorry. It will be interesting also in the context of new observations that are obtained, for instance, by astroseismology for interiors of stars for level of magnetic fields, which is important for the magnetic instabilities, and the origin also of these magnetic fields. And also, a last point I would like to say, even if we are discussing about lithium, another element which is quite interesting in this context is the question of beryllium, because for it, we don't have many constraints, but it's quite interesting because it's very difficult to reconcile actually the depletion of lithium and the depletion of beryllium. And in order to decipher which transport processes will be the good one to explain all what we see, it would be actually nice to have both the lithium and the beryllium constraint. And I will stop here. So how do you distinguish overshoot and spot activity? It will be a good question. Actually, the thing would be what would be nice would be to have more asteroseismic data, because thanks to that you can probe the stars, interiors of stars, and determine where is the base of the convective envelope, and so can constrain the overshoot. So it could be a first thing. And then for the spot, I guess you could obtain some observation for the magnetic activity. And actually, one of the next steps I should do in my models would be to consider more the magnetic field aspect. And then the thing would be to test in view of this constraint from the spot and the magnetic activity which is observed, how I can describe that in my models and what kind of prediction I would get from that. I think.
All right. Thank you all the speakers of this session. Now we have the planned panel discussion. So my panel members, please, would you come? So, please, I have a question. Can we have people go for coffee and come back, bring it here or not? So that we don't have, because we need to eat some time of the coffee break. Okay. I'm just saying because we have to eat some time of the coffee break, right? Because of the technical difficulties. So how about that? If you guys want to take a stroll, get some coffee and come back, we'll start maybe in 5 minutes. Okay, our panel discussion. And so our panel members, if you can come up here to the front, we're going to move some chairs and sit here, I think. Okay.